Tim Patterson is someone we know well. He grows a nice stash. And he's from Canadian University, comes down from Carleton, and he's a specialist in one of the areas that is used by the people in climate science to decide whether we're in a crisis or not. He talks about ocean levels. Tim.
I just have to use this cheat sheet. I'm a Macintosh user. Hit escape. Click on name at bottom. Oops, is that clicking on name at bottom? No, I'm clicked on somebody else's thing here. Oh, roll. Here's Patterson right here. Okay, right here. Just
you notice he's not looking at me to help.
Did that do anything? Oh, I've hit somebody's animations. Sorry. Here's Graham's going to help. Or no, not Graham, sorry. Yeah. There we go. Thanks very much. Okay. I didn't read all the directions there. Sorry about that. Anyway, I'm not going to talk about oceans today. Actually, most of my research through the years has either been working on marine projects or working on lakes in more recent years. But due to unpopularity at home, heading off in a ship for multi-weeks at a time and so on, and actually starting to hang out with Helen a little bit. I'm a fellow at Queen's University in Belfast, and in addition to being at Carleton University in Ottawa, she's led me to appreciate working on peat bogs. And so today I'm going to talk a little bit about another proxy that you can use to look at a peat bog, looking at stable oxygen isotopes and what information that can provide to us about paleoclimate. And it's always useful to use multi-proxies. As anyone knows who works on paleoclimatology, you want to look at as many as possible so that you can validate the results from one or the other. So Helen has been looking at sort of a hydrological response. I'm looking one that's going to tell a little bit more about the temperature. Peat bogs are very extensive in Canada, and actually I wasn't aware of this until I started to work in these things, just how prominent they are, particularly in areas such as the western part of the Hudson's Bay region and up in northwestern Canada. They're very, very extensive. And even where I live in Ottawa, so here's Ottawa is right here in eastern Canada, and here's the city of Ottawa right here. I live about right here. Here's a bog I'm going to talk about today, Bleue bog, which is, from my wife's perspective, very convenient for me to go to since it's about a 15-minute drive from my house around here. It's a large ombotrophic bog, such has been introduced by Helen already here, and it consists of these various sorts of little lobes around here. It's called Bleue, means blue seed bog, and it's interesting that after deglaciation about 10,000 years ago, this region was actually an arm of the sea. It came in here, so there was, and after the sea retreated, we had ended up with a very large river, which was enormous at that time, and the area that Bleue bog inhabits today was an arm of that river with some various islands sitting in it, and you can see these little islands. Well, I'm going to tell you about this little this area right here, which is part of a Carleton University and McGill University research station. And it's basically, the Bleue bog is also a Ramsar site. It's got a very special biota in it, and it's a protected site. It's a conservation area at the present time. And where the core is right here. And why? Part of the reason we wanted to go and core in this bog right here is, number one, is that well, the number one reason is because they had this really nice boardwalk out here that you could get by the Carleton University McGill. If anybody's ever walked across some of these bogs, it's kind of deadly. So you have this nice boardwalk that's built out here about a kilometer long, and here's all the instrumentation. These little things are kind of cool to watch when you're coring, because they keep going because they're measuring carbon dioxide flux, and there's various other sorts of monitors around here as well. There's always a crowd of people around. So this is the place that we were carrying out our core, but it's also close to places that they're monitoring what's going on with carbon dioxide and so on. I won't spend more than a moment. This is an ombotrophic bog, such as Helen has already described. Basically, it starts off as a basin, which eventually changes into a fin, which is sort of like a little pond that eventually becomes filled in. And then, over time, in some bogs, they develop this ombotrophic domed peat, where you have no inputs except for of precipitation, except coming in from rainfall. So there's no streams or anything around here. And the only extra bit that we have with the Bleue bog here is there's a marine clay at the bottom, because after deglaciation we had the arm of the sea had come in. Basically, if you're looking at what's going to influence your moisture in these bogs, the places like Helen looks at, one of the primary drivers is precipitation, okay, in these in the maritime settings. Well, here we get precipitation as well. But in the Ottawa area, what you're often recording in here is the temperature, mainly because, unlike Ireland, and like lots of places around Michigan and so on, it gets pretty hot in the summertime. And so you're often recording temperature because you have so much drought that goes on once you start to move on to July and August. So the sorts of information you get here, if you're looking at some of the proxies, is more correlated with temperature. So the whole objective of the research that's going on in this bog over here is to try and look at a very high resolution Holocene paleoclimate using oxygen isotopes, and to demonstrate then that these changes in the oxygen 18 proxy can be useful for paleoclimate reconstruction. Now, there's been a whole flurry of papers appear just in 2009, 2010, so there's starting to be more of a consensus along this line that this is a good proxy. So I think that's becoming established already. And then finally, determine what are the major forcing factors on climate that are driving climate in this region. Here's an image here of when we did the field work, and we did it by snowmobile. This was done in March 2008. This was the year that we had 16 feet of snow in Ottawa. It practically broke every record going. I don't know, how tall is this ceiling? Is this 16 feet? I don't know what. It was an enormous amount of snow. I had nowhere to put snow by the end of the winter. You didn't have it all at once. Normally, Mare Bleue Bog, they told us, they say it's a great time to go out in the winter. There's no snow. It all blows away. Well, here we were digging, and actually, I see, is that Andreas Prokop back? There's Andreas. This is Andreas standing here. He came out and helped us dig, and he can appreciate how the hard digging that we were doing. This was not the first hole we dug around there looking for these the bits and places that we were going to core. But you dig in here, the bog doesn't freeze. Okay, so there's no frost level. So about a little frost level, but it's thick, so you can quickly core in here. And what we're looking at, I don't know if you can see it. There's a little dome right in there. So we had to keep digging until we found these little domed areas. I'll talk about these hummocks and hollows. Here's pictures of the core material you take out with a Russian core, and here's at the bottom of the core, and you can see it's kind of gray here. That's the marine clays, and you can see it starts to grade out as it turns into a fin as the marine basin became isolated. And here's what we're looking for again. Here's a look in the summertime. You look for these sort of hummocks are the places you really want to core as opposed to the more hollow areas, mainly because if you go into a hollow, that might be wet all the time. And particularly it's impacting for like that work that Helen does, because you would have microfossils that, or the little microorganisms that are wet all the time, so they aren't going to be stressed, so you aren't going to get very big changes over time. So you want a little bit higher, so it might be wet for a while, but then dry other times. Here's the age model that we've developed for this core in here based on radiocarbon dates in this area. There's no tephras, unfortunately. There's no, maybe it's fortunate based on what Helen talking about her car, that we have no tephras that are dropping into our area. Well, and just to say that basically it moves from the marine to transitional to the fin, and then on up into the area of interest, which is the amphitraphic bog. And again, most oxygen 18 analysis that have been done on peats up to the present time have all been done using bulk samples. So they go in and get this nice core like this and say, oh, there's a little chunk right here, and you just take it and run your analysis on that. But there's some issues with that. That have come up. Basically, it's because the sorts of plants are going to be found within a bog. And Helen shows lots of pictures of sphagnum moss and so on, but you get lots of vascular plants around there as well. The issue here is that all these vascular plants have stomata with guard cells on them. They're taking in oxygen, carbon dioxide, releasing oxygen, and the sort of fractionation that's going on with the oxygen here results in some changes to the chemistry. And as a result, you're measuring neither precipitation or temperature or anything else. It's just you're measuring some degree of fractionation that will vary from plant to plant. So the results that you actually get by doing oxygen isotope analysis on a bulk sample is spurious for the most part. So then you say, well, you're going to do oxygen isotope. That doesn't sound very promising. But luckily for us, we have all these sphagnum moss species that are existing in these marshes. They're very, very common around here. And they do not have stomata. These bryophytes basically are very simple sorts of organisms. They have only a very limited ability to try and control the water loss that's going on within their system. And so they have to have this very simple water use strategy. And so we can take advantage of that. And basically what it results is there's a very insignificant change in the signature that's becoming from the source water that's coming out and what's eventually getting deposited in the cellulose of the sphagnum. And so basically, in these ombotrophic settings, that's where the water is just coming from meteoric sources. Remember, it's not flowing from anywhere else. You're basically getting, it's coming from the precipitation, and so you're getting the signature from the meteoric water. And basically, once you move into these continental settings, particularly at mid-latitudes, another lucky thing about Ottawa, it's at exactly 45 degrees latitude. And it's also a very continental setting, much to my chagrin. Mainly, we kind of live in this valley in the greater Ottawa area around there in the wintertime, and it's quite continental. Despite not being far from the Great Lakes, it's really continental. So the winters are brutally cold, and so I just looked down the road at Toronto, which would be very mild around there, and we're like 30 degrees colder. But in the summer, because we're in the valley, you also get these massive humidities. And I was interested to see the other day that the closest city to us as you move south with the similar humidity and so on is Philadelphia in the summer. So we get like subtropical in the summer, subarctic in the wintertime. But anyway, so we get this great seasonality, quite continental. So when you're measuring the sphagnum around here, you're really starting to measure this temperature signal in there and not the precipitation. And we also preferentially always look at the stems, and that's where you get the most closest correlation with the meteoric oxygen, or water level, sorry. Here's some of the different species we look at around here. Again, they vary as what sorts that you find as you move from up the hummocks down in the hollows. It's interesting we start to comparison between the stems from the different species, and we move down cores, do tests, they come out the same. And again, it's because we're living in this very continental setting, and so with all the droughts going on, so there's a consistency as you move from species to species. So we're very, very happy with the sorts of isotopic results we get. Here's basically showing a correlation. Then this is a curve basically then looking at the excursion of oxygen-18, looking at the enrichment of it, and basically as you move to the right it's indicating increased temperature. And as you can see from about 9,000 years ago, there's some sphagnum start to appear every so often, the temperature generally started to increase as we moved on, and then it was warmer during different parts. We can see in here, compared it with different sorts of proxies around here. Here's a reconstructed sunspot number over here. We have glacial advances that are going in different parts of the world. Here's some intervals looking at high drift indices and so on. And we can see that some of the excursion go on that seem to correlate. For example, here's one here, a North Atlantic cooling event, which started about 4,600 years ago. It seems to be quite well recorded in the record at Mare Bleue Bog. The warmest temperatures ever, it seems, in this region were shortly before that, about 5,000 years BP. That was the Holocene hypsothermal. And then some other events that were going on as well that seem to be showing up quite well. It's interesting, we have this excursion downward around here, about 40, in this particular case, about 3,400 years ago. This correlates quite well with work I've done on the West Coast, which we record a more PDO-like sort of environment at that time, and we seem to be getting cooler as we begin to develop some drought-like conditions in the West. So maybe it's suggesting some Atlantic multi-decadal oscillation influence as well, but various sorts of signals going on in the record. I'll show you a more higher resolution one in a second. Looking at that sunspot record, we do a spectral analysis here. Only a couple of really signals pop in. We have about a 1,200-year cycle, which seems to correlate reasonably well with Bond cycles, if you're familiar with those from the Atlantic. There's another very prominent cycle here at 210 years. Haven't done any wavelet analysis yet to see if there's any sorts of consistent patterns that come and go in here. That's another type of time series analysis yet. Here's a little higher resolution image right here, so you can see some of the patterns around here. Here is the change in temperature over time, again compared with the northern hemisphere reconstructed temperature. And we can see here, this matches up very well, that we move into the medieval warm period. There's quite a warm interval. Once we start to move beyond that, it starts to cool off again, and we begin to move up in here a little bit. It gets a little bit messy up in here because some of the, we collected an awful lot of samples up there, but there's an interval of the active part of the peat bog, which sometimes it's hard to discriminate what's living and not living and so on because it's not compressed yet. But the record here follows pretty well with what we know from elsewhere in the northern hemisphere. This was just emailed to me yesterday. One of Helen Rowe's students, Suzanne Elliott, is also working on this exact same core. And again, I told you about the utility of using more than one proxy around here. She's looking at these testate amoeba, or we call them in North America thecamebans. So I guess it's one of these sort of things. You say tomato and I say tomato. This one's kind of not, but they mean the same thing. That means theca with a shell and an amoeba, so the same sort of thing. But she's already just a first-year PhD student, has done an awful lot of work looking at down through these cores at different sorts of species. And here's, I just picked out a couple of species. It's interesting that she sees some things happening about the same time we do. Here's some pictures of some of these little species that are illustrated right here, that around our first big kickoff around here, we can see the beginning of the northern hemisphere drought phase, and this is about 4,600 years ago. I was picking the same thing up with the isotopic data that I just showed you here as well. Something interesting going on here, the beginning of the little ice age around here, it seemed that this region started to get drier for whatever reason, and the isotopic data was showing us that it was starting to get cooler at the same time. So and then it's interesting as we came out of the little ice age, this species right here is one that indicates drought. It's been getting drier in this region as the temperatures start to recover as well. So it's behaving a little bit differently in here than it has been before. So, so having these several proxies working together, it gives us a little bit greater confidence that the patterns we're seeing are actual. Here is a comparison in even more recent times between solar cycles and looking at the sphagnum isotopic data, and this is looking at the relative temperature changes over here. At this stage, don't really see it. Here's the spore minimum, the Maunder minimum, the Dalton minimum around here. There's not, in my opinion, yet what I consider a great kick that's coming in as we move through these minimums. Maybe we do a little higher resolution sampling. The biggie, the one that shows up the best is right around here, the Dalton minimum. But in this region, that also correlates very well with the year without summer. If anybody, you wouldn't remember that. In 1816, people still talk about it, or some people, my Fred Singer might, some of these guys. But so basically the year without summer, the Tambora eruption had gone on, and basically that whole eastern part of North America was enveloped in a gray cloud, and places like Quebec City had snow in June, and so on. So this whole region basically was a temperature decline that lasted for a few years, and so there's a big dip down in here, and then it starts to recover after that. So the conclusions is that the sphagnum oxygen 18 record that we're getting from Mare Bleue bog is tracking the Holocene paleotemperature fairly well through the last 9,000 years, and seems to be correlating well with data that we're getting from elsewhere in the northern hemisphere, particularly through the last 2,000 years or so. And it's really interesting about that low that's going along in that about the late 1818, 1820 around here. Is it the Dalton minimum? Are we looking at the Tambora eruption? So I think we're going to be looking at that in much more detail to see exactly what we're looking for and try and find a better correlation with what's happening. We see some interesting shifts here. These lower values, again, correlating with the little ice age from about 200, 800 years ago. There's a cooling pattern we see as well from 2,800 years to 3,400 years in this record that is similar to stuff we see on the West Coast. And it makes sense that we might see this in the continental record, because as we're learning more and more about things like Pacific decadal oscillation, and we're learning more about the Atlantic multi-decadal oscillation, a lot of these periodic drivers that have multi-decadal return times and driving drought cycles and so on are blowing from the west and into the more continental parts of the continent. We seem to be starting to pick this up in this continental setting as well. And we also are seeing in this preliminary data a 1,200-year cyclicity in here, which suggests again that we're probably seeing a bond-type cycle, and suggesting that even though we're in quite a continental environment in here, that we are seeing signals that are appearing, generating in the Atlantic region and have been detected elsewhere as well. So I think that this leads some possibly suggestion that there may be some solar influence as well. So. And I think that's all I'm going to have to say today. Thanks very much.